right, here we start. So the last couple of days, we've been discussing EMR, electromagnetic radiation. And 9 times out of 10, when I think of electromagnetic radiation, I'm thinking of light. Just because light's the one thing that I can see. You guys good here? Okay. So, I mean, although you guys should know about things like X-rays and UV rays and radio waves, when I think of EMR, I think of light. And I think that makes sense because light, I have eyes that have rods and cones. And you guys ever do that in biology where you talk about like why you can see? We have things in our eyes that can allow us to see light. Okay. Today we're going to talk a bit more about the idea of is light a particle or is light a wave? And the answer to that is it's both. Okay, so quick reminder of history lesson. Sir Isaac Newton, the great Sir Isaac Newton, chair at Cambridge, the most famous scientist in the world, says light is a particle. I believe that. You should all believe it too. Was he wrong? No. One of the best reasons for that is that light bounces off of things like a mirror, and the word we use for that is reflection. And reflection really would seem to mean that light is a particle. Okay. After he dies, people are more willing to challenge him, and they say, I'm not so sure about that Newton guy. He was a great guy and all, but I think light's a wave. Right? And we have some evidence of that too. And so for the last few days, we've been talking about refraction, where light can bend through different materials. And last day, we talked about diffraction and interference, which is how light can actually interact with itself. Okay. And so now I want to fast forward to the turn of the 20th century. So that's the year 1900. Okay. At this point here, here's a list of some accomplishments that physicists had gone through. Number one, Newton had explained how objects move. Basically, all of the kinematics formulas, as well as all of the force formulas that you learned in grade 11, Newton kind of mastered all of those. And maybe you know this name. His name was Johannes Kepler. You guys use him in Physics 20 as well? He studied planetary motion and figured out how to do centripetal velocity. Okay? And so they were able to now predict, physicists were able to predict where the sun was going to be in the sky, where the planets were going to be. And then Maxwell, he came up with his famous equations for electromagnetism. I don't know why I didn't finish this thought on Rutherford. So if you want to write in about Rutherford, Rutherford was about to do his famous gold foil experiment. You guys ever heard of this one? Rutherford shot particles at gold foil. And I don't know necessarily what he was expecting, but I think he expected them to just hit the gold foil and just stop. Like, for example, imagine I threw a volleyball at the whiteboard. What would you expect the volleyball to do? It would hit the whiteboard and stop. And you know what happened instead? Stuff phased right through, which was weird. He was like, why in the world is stuffing phasing through? And he hypothesized there was a nucleus, that all of the matter was like in a little core. Right? And then the other weird thing is that sometimes it actually bounced right back at him, which he didn't expect either. He figured, well, maybe if it all phases through, why does it actually deflect? So he came up with the idea of a nucleus. It was around this time that a famous scientist named Kelvin, he gave a lecture somewhere, and he basically said, physicists, good job, everybody. We have figured out the universe. Pat yourself on the back. We know everything. And then Max Planck came along and basically broke physics. And people will actually talk about this to this day, is that then classical physics began to end, and this is now the start of quantum physics. And I love this stuff. This is like why I love to teach physics, because it is weird and it is cool and it is unexplainable, and physicists are still to this day trying to figure this out. And so that's what I've got on the slide here, is that at this point, physicists, they thought they knew everything, and then there was a problem. And so I'm going to show you guys a quick YouTube clip that helps kind of explain this, hopefully. So I just got to find where I left it. It's in my videos, and it's this one here. Okay, so I want to pause for a second here because maybe that didn't even make sense just yet. So let's just do a quick recap. Okay, there's something called a black body, and I've got some slides on this coming up here in a bit. So I may as well go find those and discuss what a black body is first, because maybe that doesn't even make sense to you. So find this slide right here. I'll re-show the video in a second here. You guys have heard of a black body before, but maybe you've never used the word of it. Okay, does anybody have at their house a stove with the element on it? And when you turn the element on, it glows red. You have one of those at your house? Unless you have like a natural gas stove, right? Or this example right here. Let's say that you heated up a horseshoe really, really, really hot, and eventually it glows red. You guys ever seen this before? That's black body. Okay? It's an object that in theory should absorb all wavelengths of EMR that strike it. Okay? But as it keeps absorbing and absorbing and absorbing, eventually it's going to re-emit the EMR as a color. And what ends up happening is the black body is vibrating faster and faster and faster. Okay, let's talk a little bit of like basic grade 8 science. What is heat? Yeah, and what causes things to be hot? What's happening at a particle level? When things have more energy, what are they doing? They're vibrating. Okay, so imagine you got all these particles that are vibrating, right? But these particles, what are they made of? Well, they're made up of protons and neutrons and electrons, right? And if we can get them vibrating fast enough, they will actually give off EMR. Because what creates EMR again? Accelerated charged particles, right? So what is causing this thing right here to glow? We are heating up the particles so much that they are vibrating so fast that the charged particles are actually giving off EMR. We call those things black body objects because in theory, they are normally black in color. Okay? And what ends up happening is as we heat them, and as we heat them, and as we add more energy to the system, the energy gets re-emitted as EMR. Does that make sense at all? So now, according to classical physics, here was their idea. They figured that if you heat it up more and more and more, it should then give higher and higher frequencies. Okay? What is the lowest frequency of light that we can see? Red. Say that one more time. What is the lowest frequency of light that we can see? Red. What comes after red? Orange. What comes after orange? Yellow, green, blue, indigo, violet. And if you keep heating it up, in theory, you'd now get into ultraviolet and X-rays. Okay? So why do we see this horseshoe as red? Or why do we see the element on your stove as red? It is getting heated up so hot that the particles are vibrating so quickly that they're actually re-emitting off light. You had a question there? Oh, okay, so you just look like you had a hand question. Yeah, that's what they were expecting, is that as you increase your intensity, what should happen is your frequency should also increase as well. That's what they expected, is that if you make it go hotter and hotter and hotter, the frequency should have a linear relationship. That's what they expected. No, red is a lower frequency, is it not? It's a higher wavelength, but the lowest frequency is like low frequencies would be radio waves and microwaves. Quick review here, right? Here you've got your spectrum. You're getting I think you're getting frequency and wavelength backwards, right? Over here, this right here is a higher wavelength and a low frequency. And over here, these guys have a high frequency and a low wavelength. So then this is red, orange, yellow, green, blue, violet. So the first one that we can see then is red. But as you heat things up, it said that in the video. Did you guys catch in the video? They said like you heat things up, it goes from red to yellow to blue and white. Right? You ever heard the phrase like white hot? Right? Or maybe you can even see a flame, right? Shoot, I give it back to Janae. Grab a lighter, right? And hit the flame on the lighter. You ever seen the flame become blue? That's hotter there, right? As opposed to yellow or as opposed to red. Okay? So white hot, if you can make it turn white, that's actually the hottest of all of them. One of the reasons why is it's actually combining all of the wavelengths together, and they're all merging. Yeah. Just that was the idea. So let me elaborate on that idea. The question is then, well, how hot would you have to heat it? Well, that's your intensity, basically, right? On this axis, I stood for intensity, and they figured if you just heat it up hotter, wouldn't that give you new colors, right? Wouldn't it just keep going on and on and on for forever? Okay, so that's the idea of a black body. The idea that a black object, it's typically a black object. You heat it up, and it starts to glow different colors. Heat it up hotter and hotter and hotter, it's going to shift what color it is. Okay. Brief side note, it's actually how we figure out how hot the sun is. What color is the sun to us? Yellow, right? And so a red sun probably isn't quite as hot as a yellow sun, right? And if we see things in outer space that are blue colored, those are probably even hotter still. Does that make sense at all? What was that? Yeah, but that's not because they're emitting light though. Like the sun is actually producing the light. That's just the color that light reflects off of it. Like your shirt is blue, right? Is your shirt producing energy like the sun is though? No. So the only reason why it's blue is that that's the wavelength that's absorbed versus reflected. I actually have a slide on that. Let me show you that slide. Well, let me go through my slides here. I'll go back to our video. Here's the same concept. Okay, you heat this up to 900 Kelvin, it starts turning red. You heat it up to 1750 Kelvin, now you start to get like yellow colors, right? You heat it up to 5500 Kelvin, well now it's white and blue. Right? You guys have seen this before, I'm sure, you just didn't know the words or theory behind it. Why is this happening then? Atoms are vibrating so quickly that it's actually re-emitting radiation, but in the form of light. Okay. Here, can I go to this slide right here for a second? So you asked about like Neptune being blue, right? Why is your shirt or Neptune blue? It has to do with what colors get absorbed versus reflected. Okay. Black absorbs all wavelengths. That's why we see it as black. All colors come in and hit black, and nothing gets reflected. Why do you see something as red then? All the colors come in and hit a red surface, and the only thing that gets reflected off of it is the red wavelength. That's why you see it as red. Okay, so why is Neptune blue? Well, when the light from the sun hits Neptune, all of the wavelengths of light, red, orange, yellow, green, blue, purple, right? All of them hit Neptune. The only one that bounces off of it is the blue wavelengths. That's what we can see. Okay, I mean, when we're talking things in outer space, there's some other factors here too, but does that make sense though? White objects, everything bounces off of it in theory. Okay, so let me go back now to this video with a little more context. Maybe I'll rewind it. Hope this will make sense. Let's start here again. Oh, I missed it there. Hang on. Okay, so what they're saying right here is imagine that you wanted to figure out what temperature it was inside that furnace there, but you didn't have a thermometer, right? So there's a fire inside that furnace. We want to know its temperature, but you can't measure it based on its thermometer. You could measure it based on what color you see. Does that make sense? So if I saw a blue flame versus a red flame, I would now be able to estimate the temperature. Does that make sense? That's what they're talking about here. So what's he doing right now? We're heating it up. Right? The particles are moving faster and faster and faster, so fast that they're actually re-emitting radiation, right? It's absorbed heat, and that heat is causing the particles to vibrate and give off the color red. Okay, and because they knew what color it was, now they know the temperature. Does that make sense now? So that's black body radiation. Okay, So what they're discussing here is particles. Particles have size to them, right? And at a certain point, I can't shove any more particles in there because it's so dense. And then when they vibrate, there's kind of a limit to that. You get what I'm saying here? If I put particles inside there and try to heat those up, there's kind of a limit to how much you can put in there because they have mass, they have size. Okay, so here's where I pause the video because hopefully this will make more sense now. Now what they're going to do is they're going to try to take waves and consider how waves work. See how they're getting more and more squished? Okay, so let's pause for a second here because they're kind of being silly. But let me kind of describe the idea here. On a previous slide here, I had drawn something that looked like this. As you increase the frequency, in theory, you should be able to just keep going and going and going, right? So let's talk about your your spectrum. First, there's red, orange, yellow, green, blue, purple. So let's say you heat something up so hot that it glows blue. We're still safe. But what if you keep heating it up? Well, then it would go ultraviolet. Ultraviolet's not necessarily good for you. Ultraviolet causes cancer. Let's say you keep heating it up more than that. X-rays. Well, this causes a problem because if matter truly worked this way and you kept heating things up as you increased your frequency basically got higher and higher and higher, we'd all of a sudden get to the point where like you could heat something up so fast that you get X-rays, and that's not what happens. So there's actually a slide in my notes here that discusses what actually occurs. You would expect that the intensity and the frequency to keep having this linear relationship. And for whatever reason, right about here in terms of frequency, it all of a sudden just drops off a cliff. And it made no sense to anybody, right? This is red, then it's yellow, then blue. If you just make it hotter and hotter and hotter, the frequency basically would match it, right? Keep going, you expected to now get UV rays and X-rays. And it didn't happen. Okay, let me just keep showing the video here, I think. Okay, so here's the formula we're going to use in a bit. Let me rewind to some stuff that maybe didn't make as much sense. I just want to find it here. Where was it? Okay, this picture in the background. Give me a sec here. Okay, so do we all agree that electromagnetic radiation, that's a form of energy, right? EMR is a form of energy. Light is energy, right? And the idea basically was, well, why can't I just keep squishing these waves smaller and smaller and smaller, right? Now, if I keep squishing these waves smaller and smaller, what's that doing to the frequency? Increasing the frequency, right? As the waves get smaller and smaller and smaller, the frequency increases. And what they expected to have happen is that then it would start giving off red, orange, yellow, green, blue, purple, then ultraviolet, then X-rays. And that's not what happened. And they couldn't explain it because they're like, well, why can't you keep squishing these waves smaller and smaller? And so Planck had an idea, which was a little bit further in here. Where's the picture? Here it was. He suggested that although, yes, it comes out as a wave, perhaps these waves, they come out in smaller, discrete packages. Okay? Let me give you a different analogy. Okay? In chemistry, the smallest thing in chemistry we usually discuss is an element on the periodic table. Okay, technically I know we can go smaller than that, but does that make sense how that's kind of like the smallest thing we kind of work from in chemistry? In biology, what's the smallest thing we work at in biology? Usually a cell. Now, technically the cell has nucleuses and nuclei and mitochondria inside of it, but we consider that to be like the smallest unit of something. But in physics, up until this point, we kind of just assumed that energy can always just be smaller and smaller and smaller. And Planck kind of suggested, what if there is a smallest unit of energy? What if you can't have half of a something, right? Now, let's say, what's the unit we use for energy? Joules, right? What Planck suggested is, what if you can't have half of a joule of something? What if there's like a limited smallest packet that something could come in? And the word he used for that was quantized, where there's literally like, there's no in-between values. And then he did some calculations, which we're not going to do, but when he ran those calculations, it actually worked. And it basically suggested to him that energy comes in like small packets and units. And guess what this meant? I'm going to go back to my notes. I think I'm done with the video now. I'm going to fast forward here. This was called a quantum, a small packet, basically a minimum amount of energy. You can't have a smaller amount than this. In the same way that you can't go smaller than an element, and you can't go smaller than a cell. Okay, I know that's not true actually, but that's what he suggested. And later I'm going to talk about Einstein. I know I'm jumping ahead here, but Einstein built on this, and he went back to the idea of saying, well then, what if energy isn't a wave? What if energy is a particle? And it can only come in smallest units. Okay, I want to show you guys a quick demonstration. This is cool. I like this. Hopefully the flash works. If not, UV, I need your help. Okay, so here's a camera. When the camera flash goes on, there we go. Okay, when the camera flash goes off, you guys agree that's a form of light, right? Now, they've been debating, is light a particle or a wave? Okay. You're going to have to listen really carefully because it's not that loud, but if something even just slightly hits this, can you guys hear that resonating from where you're at? If not, come closer. Here. I'll just do a slight tap here. You can hear that. Okay, listen to this. Can you hear that go off? I can make the symbol resonate just by taking a picture of it. What happened is the light is actually behaving as a particle, and the particle is hitting the symbol. I don't know that you guys can hear that. Can you? Or should I come closer? I'll do a full flash again. Here, let's just come in small groups here. You got to come closer here. Okay, just listen really carefully for when the light hits it. Did you hear that? I didn't hit it. Come on, flash. You heard that there? Okay. So that's a great example of what Einstein eventually quantified. He gave a name to it. He said, what if energy what if energy isn't just a wave? We know that energy can come in wave forms, but they cycled back to where Isaac Newton started. Believe it or not, Newton was, I mean, he wasn't wrong, and neither was everybody else who said that light is a wave. It's actually both. It actually has both wave and particle properties. And what you were hearing there was light particles hitting the symbol and causing it to resonate. We have a name for that. I know I'm way out of order on my slides here, but this is called a photon. Einstein basically gave a name to that. And basically the idea is that these individual energy packets are hitting the surface of something, and that's why it's resonating. This like blew everybody's minds, and it still kind of does today. The idea that like, well, is light a wave or is it a particle? It's both. It behaves as a wave, and it behaves as though it's a particle. There are some physicists who've actually worked on trying to figure out what's known as the rest mass of a light photon. Okay. The reason why they call it a rest mass is that by virtue of it being light, it's in motion, right? Like it's moving. And what we'd like to figure out is that if we could stop a light particle from moving, how much would it weigh? And like it weighs something like to the minus 40 kilograms, like it is ridiculously light, like half the size of an electron even. But that's basically where quantum theory began. And so Max Planck's idea of energy being in packages or particles is where I want to go to. Does that kind of make a little bit of sense here? Okay, why don't we take our break right now? Because I promised you that break. So maybe come back in 2-3 minutes here. I got more YouTube videos, and we do have math equations to get to in a bit, but why don't you guys take a break now? Because it's already been a while. So come back in 2-3 minutes. We're going to get into that in the next topic, where it's actually almost impossible for us to calculate these things. Yeah, so what ends up happening is we've now discovered that observation affects your measurements. Just merely by looking at something, that light causes it to now be affected because light's actually a particle and a wave at the same time, somehow. Okay, so we want to, like this, you use 200 as though as a frequency. Well, no, this is a megahertz. And a mega, yeah, so it is a frequency. But mega is this guy right here at 10 to the 6. So you need to add 6 more zeros afterwards. That's your frequency. Yeah. Now, here's the thing, though. When you times that by 60, the wavelength, that's where the problem is that this isn't the right formula then. Because the 60, it's how many wavelengths you have, as opposed to like what the wavelength is. Well, it's still that formula, but backwards. We actually know the velocity. What is the speed of your frequency? It's 200 megahertz, but that's an EMR wave. What's the speed of any EMR wave? The speed of light, which is written on here. The speed of light is 3 times 10 to the 8. That's V, yeah. So we actually know the V. It is, yeah. All electromagnetic radiation travels the speed of light. Okay, now we still know the frequency, so that the equals is still going to be that 20 million number, something like that. Here's what we need to do. We need to solve for the wavelength. Yes, we're going to solve for wavelength. Now here's the thing. Once we know what one wavelength is, it says there's 60 wavelengths. So all you got to do is just times your answer by 60. 60 is not... Okay. Yep. V by F, yep. No, the 3 to the 8 divided by the 200 number. Perfect. Okay, so this is now your wavelength. This is one wavelength. So then you need 60 of them. So if one wavelength is 1.5, then how many is 60 of them? There you go. And then this answer should be in meters now. exactly. That's how far your garage opener works. Did that make sense about wavelengths and frequency for you there? Because I feel like you had those backwards. Is that was what the case was? Okay. Okay, so you're just backwards on your spectrum. Okay. Okay, yeah, because it goes, what is it? Radio, micro, infrared, red, orange, yellow, green, blue, violet, ultraviolet. So you just had the middle part backwards? Okay. Okay. Okay, guys, why don't I start up again here? Let's watch another one of my little video clips I've got. Before I can get to all the math equations, I really want to make sure you guys understand all the theory behind this. And this is weird stuff. Yeah, it is confusing. It's okay if you're looking at me going, Chris, I don't get it yet. Like that is normal for physics. Okay, I get that. Maybe for the last 11 years, normally when a teacher talks to you, you go, yeah, I get it right away. It's okay if you don't get it right away. That's like we're rapidly reaching a point where like I don't understand past this level, and I'm okay with that. Because if I did, I wouldn't teach high school physics. I would be at MIT, and I'd be one of like the 100 people in the world who gets quantum stuff. You get what I'm saying here? Like, that's what makes this stuff so cool, is that it is challenging, and that it is hard to wrap your head around. How do you wrap your head around light being a particle? I can't hop on the magic school bus and zoom down to size, right? So it's very abstract, the stuff we're doing. So, okay. Anyways, everyone's back here. Let's watch another quick little YouTube video on black body radiation. Okay, let's make sure we caught that. Why would it become invisible? Because I can see red light. It goes past purple, right? That's as far as our eyes can see, right? And so if you kept heating it up further and further and further, eventually we wouldn't even be able to see it anymore. But is that what happens? No, right? Because like the sun doesn't all of a sudden just disappear on us and become invisible to us, right? So that's what he's going to discuss here next. So I'm going to leave it here for a second. So here's what Planck suggested and said. Apparently, light's not behaving the way we expected to as a wave. So he said, well, what if it's coming as a particle? What if light is a particle, just like when I shot the camera at the mirror, and you can literally hear it clanging, the light particles clanging off of it, right? He suggested maybe energy comes quantized, hence the name quantum. Okay. Here's the formula we're going to start using. Basically, the idea is the amount of energy that you have is based on the frequency, but times by Planck's constant. Now, I don't even want to do any math yet on this here, but look at how small Planck's constant is. It's 6.6 to the minus 34. So imagine you have a frequency of light, and you then times it to the minus 34. How much energy are you actually going to have? Is it going to be a lot or a little bit? Just a little bit. And that's what this tells us, is the energy is then coming in like discrete packets. Okay. Let's try some math equations on this. Let me find my notes again here. I'm going to kind of hop ahead a little bit here. Okay, let's try some questions, if you guys can find this bit here. So the question basically is, determine the smallest amount of energy that comes from a light source emitting this frequency. Okay. This is about as easy as it gets. There's literally one number that we have. Planck's formula was this. The amount of energy you get in the smallest packet you can have is equal to his constant times the frequency. His constant is on the other side of your data table, by the way. His constant is 6.63 times 10 to the minus 34. Can you guys find that value? 6.63 times 10 to the minus 34. And the units for that are joules times seconds. This is a very, 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 very tiny constant. Okay. What happens then if I then multiply it by my frequency, which was 4.50 E14? What's the unit for a hertz again? You guys remember what a hertz is? It's like 1 over a second. Hz is the unit we give for it, but like it really means like 1 divided by seconds. The reason why I want to point that out is, can you see how the seconds here is going to cancel with that one there? So, someone help me out here if you have a calculator nearby, because I've missed mine. What is 6.63 E minus 34 times by 4.50 E14? Yeah, there we go. 2.98 times 10 to the minus 19. And so here's what Planck basically suggested. He suggested that energy has to come in like small increments, so small that it comes like this. So again, with my analogy, we kind of assume that like the smallest thing in chemistry is an element and the smallest thing in biology is a cell. Well, we've always kind of maybe figured up till now that energy, you can always just have a smaller amount of it, or a smaller amount of it, right? Just cut it in half, use half as much, right? But Planck's idea was, no, you can't even cut it in half. This is as small as it gets. And so that's his suggestion, is this is how much energy is coming from that light source. And it's such an incredibly small amount that we actually don't even use joules anymore. A joule is such a ridiculously big unit in comparison that we use what's called an energy volt instead. That's what EV stands for. Do you guys remember doing this previously, EV, energy volt? So, sorry, what did I say? Yeah, electron volt, sorry. Sorry, it is electron volt, and it is a measure of energy, okay? Basically, it's how much energy an electron has moving 1 volt. Thank you, guys. Sorry, I screwed up here. So let's try the exact same question again, only now rather than measuring it in joules, I'm going to measure it in electron volts. Okay. Now, one more thing. I'm actually going to give you a wavelength instead this time, just to mess around with things. But do you guys recall this formula, V equals frequency times wavelength? You guys know that universal wave equation? If you ever have a wavelength, you can solve for a frequency if you know V. What's the velocity going to be? The speed of light. Yeah. Now, sometimes rather than using the speed of light, we change out this V and we put the letter C there. And what ends up happening is we merge these formulas. And if you look on your formula sheet, you might see this formula here. E equals H times lambda over C. Nope, I did that backwards. It's C over lambda, isn't it? Is that one on your formula sheet? There it is. Yeah, it's in the top right-hand corner. If you guys are looking for it on your formula sheet. Okay. All we've done is we've rearranged this formula here for frequency and shoved it in that equation there. So based on what I have now, I have a wavelength, which goes here. I know the speed of light, and I know what Planck's constant is. But this time, rather than using the Planck's constant number, 6.63, which gives us a joules number, it may be more useful to use the electron volt Planck's constant. So if you can flip over to the back side of your page, Will, I'm going to steal yours again here. Can you guys find how there's two different Planck's constant values? One is 6.63, but the other one is 4.14. I'm going to use that one, 4.14. And the units now are electron volts per second. It's a much smaller unit of energy. I'm going to times it by 3 times 10 to the 8, because that's the speed of light. And I'm going to divide by the wavelength as 212 e minus 9. Where'd the minus 9 come from? It is a nanometer. Nano is minus 9. So this is going to functionally give us the exact same information, only rather than telling us how many joules is the minimum amount of energy being transferred, it's now going to be measured in a much smaller unit. It's now going to be in electron volts. Did I forget that? Thank you. Good call. I'm getting ahead of myself. There's a minus 15 here. Thank you. For which one, Milo? Sorry, which one? This one down here? Or this one up here? Yeah. Okay, because it's a nanometer, and a nano on your sheet is minus 9. Okay. Yeah. Oh, this one up here? Sorry, let me write this again. Apparently I really just suck at writing today. Let's do this one again. Okay, so H was supposed to be, what is it, 4.14? E minus 15. C is 3E8. That's the speed of light. And on the bottom it was 212 E minus 9, because nanometers is minus 9. Does that make sense there? Again, I don't have my calculator, so if someone has calculated this, can you let me know what you got? Yeah, this is the Planck's constant, but this is now the electron volt Planck's constant. It's already been done that, basically. That's the difference between the two constants, is one of them has been times by the 1.6 minus 19 number. Yeah, it's already done it for you. Anybody else get 5.86? And literally just 5.86, right? Okay, and so that would be an electron volt. Basically, the idea here being that now we're measuring things in like smaller units, right? So rather than having like to the minus 19 joules, now we have like a certain amount of electron volts. Here was the idea then. Okay, this is going to sound contradictory because clearly you have different evidence here. But like his idea was that you can't have half an electron volt. You either have 1, or you have 2, or you have 3. But like that's the smallest package you can have. Does that make sense? Okay, although it's not the electron volt we're using, but that was kind of the concept. And I've got another video here that hopefully will help reconsolidate this idea. So let me show one more YouTube video here. Just got to find where it is again. I need, is it this one here? Yeah. Okay, this is a little bit longer, so you have to bear with me.
was important because scientists realized that this discovery made it possible to measure the temperature of an object from a distance. They could measure the temperature of the sun, for instance. During these discoveries, they also noticed that some of the objects absorb light extremely well, almost perfectly, in fact. They were called black bodies because they absorbed virtually all the light that was shown on their surfaces. These same objects also radiated almost perfectly, and as noted before, the temperature of the black body object determined the distribution of colors or wavelengths in the emitted light. This curve shows how much light of each color is emitted by a cool object. As you can see, there isn't much light, and what light there is mostly runs out past the red end of the spectrum, in the infrared. The figure on the right will show the different colors added together as we progress. Right now, only red light is visible. This curve shows how much light of each color is emitted by a medium temperature object, and the most light is emitted in the orange, yellow, green wavelengths. So now we add orange, yellow, and green
This graph is wavelength, not frequency now, hey? Yeah, so it's not the same graph I showed you before because wavelength's on the bottom.
combinations so
Right.
far
That's
with
why it's a
light.
slightly different graph.
This third curve is for a really hot object. Lots of light, and with most of it being emitted toward the blue end of the spectrum. And as you can see, our cauldron now is pure white in the center where all the colors overlap.
That's why we call it like white hot, because it has all of the colors mixing
A
together.
heated black body follows this color path as the temperature rises. A good example of black body radiation is the heat inside a kiln. Inside a kiln, electromagnetic radiation, light and heat, exist in a form of standing waves. Waves that, like the vibration of a guitar string, are attached to both ends. The ends of the standing waves, like the ends of a guitar string, do not move. They are anchored to the sides of the kiln. And many, many waves exist with varying wavelengths of color. At low temperatures, the primary color inside the kiln is the infrared, and we cannot detect it with our naked eye. But as the temperature rises, the kiln begins to glow red, and as the temperature continues to rise, the dominant color changes to orange, then yellow, then bluish white. The distribution of energy and light shifts to shorter wavelengths as the temperature rises. But there was a problem. The scientists expected the distribution of emitted light to continue, to increase at wavelengths toward the ultraviolet end of the distribution. It didn't. Instead, there was less and less light given off as they moved further and further into the ultraviolet. This was called an ultraviolet catastrophe. But it wasn't a catastrophe at all. It was the beginning of something remarkable. A truly great scientist named Max Planck soon figured out a way to explain the observation. He concluded that the energy contained in the standing waves inside the kiln did not and could not possess just any and all different amounts of energy. Instead, the quantity of energy these standing waves possess had to be limited to a few specific discrete values of energy for each color. A standing wave of blue light, for example, can have energy equal to 0 electron volts,
Okay, so I found what I'm looking for here. Maybe this analogy right here will work. Okay. What was that? 3 come from? Okay, so they were just using that as a hypothetical example, right? So basically the idea is that it has to come in like a smallest amount. It either comes as 3 or 6 or 9, and that was their hypothetical example. It could have come as either 2 or 4 or 6 or 5, 10, 15. You get what I'm saying here? Like, if energy has to be quantized and there has to be like a smallest amount of it, I don't know what the number is. Okay, so ignore the number, but like it always has to be in a multiple of that, right? So they used 3 as their example. You can either have 3 electron volts, or you can have double that, 6, or you can have triple that, 9. But you can't have halfway in between. Here's my analogy. You can either have 1 cell, or you can have 2 cells, or you can have 3 cells. You can't have 1.7 cells. Does that make sense? You can either have 1 calcium atom, or 2 calcium atoms, or 3 calcium atoms, but you can't have 1.347 calcium atoms. And that's what Max Planck basically came up with, is it had to be in a multiple of something. In this example here, they just used 3 electron volts. But that was his idea. There's got to be a smallest amount out there somewhere, and you cannot go smaller than that. And that's what changed everything, because that was the idea of a quantum. Okay? You actually have a limit to how much energy you have, not on the high side of things, but on the low side of things. Okay, so let me keep going in my notes here, because I've got 25 minutes left here, and I got a lot I want to do. So hopefully I don't rush too much. So basically, Einstein builds on this idea. And he says, okay, I think you're right. I think that light is not actually a wave, but there's actually pieces to it. And depending on what frequency you have, that depends on how small the pieces are. So if you have red light, they come in like 1 electron volts. If you have green light, they come in 2 electron volts. If you have blue light, they then come in 3 electron volts. Can I say that again? So depending on what frequency you have, if you have red light, the smallest amount is a 1 volt package. If you have green light, maybe they come in 2 volt packages. And blue then is in 3, right? And that's where that relationship came from, is that the amount of energy you have depends on Planck's constant and your frequency. So if you have a higher frequency, it comes in a bigger package. If you have a smaller frequency, then it comes in a smaller amount. Okay. So basically what I want to get back to here is then we're back to saying that light is like a particle. So let's try some examples here for the math, because although the theory is very challenging, I mean, this blew the minds of Albert Einstein. So if right now you're saying to yourself, Chris, I don't get it. Guys, Albert Einstein's one of the smartest people we ever knew, and it took him years to wrap his head around this. Okay, so don't freak out if you're not getting it immediately. Okay, but basically, let's try another example. Let's figure out how much energy a single photon of red light would have with a wavelength of 600 nanometers. Okay, so using the exact same formula, let's use E equals H times F. Except I need to know frequency, and I've been given wavelength. So let's use the alternate formula, E equals HF over, no, HC over lambda. There we go, thank you. And because measuring things in joules is often just, it's too small to measure it in joules. Let's measure it in electron volts. Okay. So if I measure it in electron volts, it's the exact same formula we just did. It's 4.14 E minus 15 times 3E8 divided by 600 E minus 9. This is how much energy a single packet of red light carries with it. So I borrowed Marin's to hope she did it right here. A lot of pressure on you. She got 2.07. Anybody else get that? Okay. This is basically the idea of a quantum now. Everything has to come in multiples of 2.07s. Okay. So Malik, you asked a few minutes ago why 3. They just picked a random number. But for this wavelength of light, the smallest package of that photon comes in 207s. Depends on the frequency, right? So red light has different energy than blue light, and blue light has different energy than X-rays. Right? So the higher the frequency, the more energy there would be. That's basically what he figured out, right? If you have a higher frequency, there's more energy. Doesn't that make sense, though? What are the highest frequency waves we have? Gamma, X-rays, and UV rays. Why are they so damaging to humans? Because they come with so much frequency, and when they come with so much frequency, they come with so much energy as well. Well, so that's what I want to get to here. This is what one photon does. A single photon has 2.02 electron volts. Okay? How often are you going to have one photon of red light come, though? Well, probably not, right? You're probably going to have thousands upon millions of photons, right? Which is why we normally times this number by how many photons there are. And because there's usually billions of photons, you're going to get quite a bit of energy, right? But what he's suggesting is if we could hop on the magic school bus, look at light, and figure out what that one smallest individual packet is, it would be this much. And so it just depends on the wavelength. So let's try the next example. The human eye is capable of detecting as few as 500 photons of light. So let's figure out how much energy your eye can detect if the wavelength is 510 nanometers. If the wavelength changes, this electron volt number will also change too. Okay, so let's try this one again. It's going to be E equals hc over lambda. So it's still going to be 414 E minus 15 times 3E8 divided by, and in this example here, it's 10 E minus 9. Sorry, my writing's not very good here. So red light comes in multiples of 207s. This wavelength right here is going to come in different multiples. While some people are doing their math equations, if red is 600, what is 500 going to be? Estimate. Yeah, orange or yellow maybe? Okay. Orange or yellow is like further along the spectrum. It should have more energy. Do you have a number for me here? Perfect. Let's call it 44. 2.44 electron volts. So that means that this was red light. Red light comes in packages of 207s. This could be yellow light. Yellow light comes with more energy in its package as it like groups together as the smallest photon you have. But do you ever just have one photon? No, right? So the human eye can detect at least 500 photons. So all we need to do now is just times by 500, and that'll tell you how much energy your eye is sensitive to at the least amount. So times it by 500, let's call it 1.22 E3 electron volts. Now, do we notice the quantization of energy? Well, no, because we're always noticing so many particles that it doesn't look like there's like individual bits there. It just looks like one big spectrum. But that was basically Planck's revolutionary idea, is that energy comes in a smallest amount, and it cannot be smaller than that. Can you have yellow light with an energy volt of less than 2.44? No. It's either going to be 2.44, or it's going to be 4.88, or it's going to be whatever the next one is. But it's got to be in those multiples. Give me one more thought here before you ask your question. It's very similar to the Millikan experiment. Do you guys remember how we learned that Q was equal to 1.6 times 10 to the minus 19? And that is as small of a charge as you can get. It has to be in multiples of that. Same concept. There's nothing smaller than that. Yeah, what was your question again? Yeah. Right. Because either you have a different frequency of it, or you have more than one. Right? So like in this example up here, I found for one photon, and this example up here I found for 500 photons. So sometimes we have more, like this light right here, you know how you have a dimmer switch? And you can like make more or less light come out of it? Right? That's basically timesing by this number right here, how much of it there is. Light. In this example, it was yellow light. Right? I've just kind of assumed it was yellow because the wavelength is less than, like red is 600 or 700, so yellow is probably 510. Depends on what type of photon we're talking about. right? If we're talking about a photon of red light, it has different energy than a photon of X-rays, which is different than a photon of radio waves. Yes. Depends on the frequency, right? So the smallest unit, it can be, but it depends on what wavelength you have, though, right? So like if you have red light, this is as small as red light can get. But if you have, for example, a radio wave could be smaller. Does that make sense? But like red light comes in packets of this. So it depends on what type of wave you're talking about. Yeah, so if you want to change, if you change its frequency, you can have different sized amounts, right? So, I mean, as another example here, red light comes in packages of this, yellow light comes in packages of this, but like if you want to have a smaller number than this, then use radio waves. Radio waves could come in a smaller package than that. Does that make sense? So although, yes, the number can keep getting smaller, the number is limited based on the frequency that you're using. So that's where this formula comes in. Based on your frequency, there is a smallest amount of energy you can have. You want to have a smaller amount of energy, just use a smaller frequency then. Yeah, there's actually cosmic. And what ends up happening, though, is that what you've got there is such a high frequency that you got such a high amount of energy. And that's why those are dangerous, right? Because as the frequency increases to ultraviolet, to X-rays, and to gamma radiations, why are those dangerous? Because when the frequency is higher, the minimum packet that it comes in has more energy. And that energy that hits you does bad stuff because there's more energy to them. That's basically the idea is that, I mean, we can't even measure those anymore, right? Because once it gets to cosmic rays, like we don't even have the ability to measure those. We're eventually going to talk about wave-particle duality and how humans actually matter itself and gives off wavelengths so small that we can't even notice them. Like we don't even have the instruments techniques small enough to actually to detect it that small. That's a good question though. This is a challenging lesson. And guys, there's a reason why this is challenging. When Max Planck discovered this, people don't use this phrase lightly. He broke physics. And there used to be classical physics, and now we live in a quantum world where physicists today, they struggle with these concepts all the time, and it takes a long time to wrap your head around it, even if you're able to. There are some things that like I don't even think I fully get. I can explain it, but I don't even fully like internalize it because it just doesn't even make sense. It's not logical. So please be patient with me because like this is hard stuff now. Not that it wasn't hard before. No, it doesn't expect its speed, though. Good point. Yeah, its speed is always going to travel the speed of light. But the amount of energy that it comes with differs. And that's actually, that's our next point here. Okay, let's do one more example here, and I might have to just continue this tomorrow. But you actually caught on to what's going to be the next thing we talk about. So if I don't have time to finish it today, can you somehow remind me of that idea tomorrow, that speed is still the same? Let's try one more example here. Let's say you have a laser. Okay, a red laser, like say my laser pen. Okay. It has a frequency that's listed, and it tells me its wattage. Okay. I can actually figure out how many photons of light there are. Okay. Let's try this example here. The formula is basically this: E equals HF. That's the formula we've been working with all this time. However, one of the formulas that was in one of our videos, sometimes there's a little bit of an alteration here. Sometimes what they do is they make it NHF. And N stands for the number of photons that you have. You know how in one of our last examples we times by 500 photons? Okay, normally we don't times by 500 because we're just talking about one photon. What is the smallest energy that individual packet comes in? Okay. But here we're going to use the formula NHF because we're looking for how many photons there is. Okay. Now, again, I can plug in some numbers here. I know N. Right here, this number is a Hertz number. I can plug that in for F, so I can plug this in as 4.38 E15. That's my F value. Here's this thing that you guys are always going to have to debate. What H value should you use? Should you use the electron volt value, or should you use the joule value. Okay? And I'm going to come back to figuring out H in a second, because the other thing I don't know is energy, at least not yet. But right here I gave you wattage. We haven't used this formula in a while, but do you guys remember the formula that involves watts? What is a watt a measure of? I heard it. Okay, so the formula for power is equal to work divided by time. But what is work also equivalent to? Force times distance, or change in energy. So I could change this to energy right here, and through a little bit of algebraic manipulation, power times by time is energy, and energy is what I'm looking for up here. See how that works? So I'm going to like rearrange my formula here and change this guy to power times time. Yeah. And so if you guys heard their little conversation here, I think you'd be probably asked, what's the time? 1 second. Because let's see, if you let your laser run for 1 second, how many particles will shoot out of it? As opposed to if you let your laser run for 20 seconds. Wouldn't there be more particles of light shooting out of it? So this is 1 second. That's the clue now to how we're going to figure out which H to use, because this gave us milliwatts. Okay, watts is going to convert effectively to joules once we do this, because this is going to be 4e minus 3. See how there's a milli in front of it? Okay, times by 1 second. This is not my greatest writing here. This is 4e minus 3 times by 1 second. And the units for watts are going to be joule units. So this is the answer to the question, which H value should you use? You should use the one that comes in joules, because a watt was comprised of a joule. Is that logical? So we're going to use 6.63 e minus 34, and then now we should just be able to algebra this and solve for n. So divide both sides here by 6.63 e minus 34, and 4.38E15. So do that on both sides, and it'll get me an N value. So this is 6. My board's not writing very nice right now. I apologize. 6.63E minus 34, and that's a 4.38E15. Whatever that is, should give me an N value. You have an N value here? I got 1.377 off Will's calculator. Anybody else get that value? Okay, brief aside, and then we're going to have to call it quits for a day. This is a long lesson. I kind of warned you in advance, eh? I just picked random numbers to make this equation. I just randomly picked 4 milliwatts and 5.38 hertz. I did not do that well. Can someone explain to me why this answer is not logical? Why is an N value of 1.377 not logical? Because it should have been a whole number. Because you can't have half a photon. Okay. Now here's the reason why it was like that. I just randomly picked numbers. Does that make sense? When I made this question up, I just randomly chose some hertz, randomly chose some milliwatts. But if we believe to be true what Planck discovered, is that you can't have part of a number, right? So I think this is a good place to spot. Well, no, it should never be rounded. It should have been either 1 photon or 2 photons or 3 photons, but you can't have half of one. Okay. Can you guys give me one more minute to explain what Jaden asked about here? We won't take any more notes here. We're going to have to pick this up next day. But give me one more second just to talk about something, because this is a good natural, like, how do I describe this? Segue, and we'll finish this tomorrow. Can I have one more minute, guys, and then we'll pack up? Okay. What we heard on the symbol then was a photon of light hitting the symbol as though it was a particle and causing it to resonate. This is what you're going to do your research project on. Scientists and engineers have discovered how to use this principle to make electricity. Let me see whether I can describe this today, and then we'll build on it tomorrow. If a photon of light, which granted is infinitesimally tiny. But if a photon of light were to hit some metal, you know what metal has on it is electrons. Oh, shoot, I'm going to run out of time here.
Could we have the following Photoelectric for items of messages? Sarah White, Aaron Ferguson, Livia Protein, Levi Newton, Gerald Samuel, Fatima Ali, Sheldon Smith, the office for messages. Thank you.
All right, last thought here, guys. If a photon of light could hit a metal surface, because it's a particle, it can actually bump electrons. Oh my goodness.
Also,
Bumping electrons causes electricity. This is a solar panel. We'll pick that up tomorrow. Sorry, guys. This is how solar panels work, basically. Okay, we'll talk to you guys tomorrow.